So here is our done Spider World game with full functionality. I'll walk through the first level to show what we've implemented. So first we can drag and drop blocks like this, and we can select color by selecting the color icon within the actual block icon. And so we want green, and we can keep stepping, and then red, and then we can choose to run. It shows how far we've gone so far. And then we can reset the world and then keep adding blocks. Oh, step twice. Step one time. And then whenever the level is completely succeeded, we can proceed to the next one. And we've implemented all 15 levels. And I can show level 11 for loops. And we can choose to get rid of blocks either using the trash can or the reset button. So show trash can. And then for reset, that. And then for loops, we can add blocks into loops by dragging the blocks to the loop icon. That's select. Run. There we go. We got the pop-up. And then we can also remove blocks as well. And then onto the presentation. So in our first sprint, most of our tasks were left in testing for a majority of the time, and we only completed all of them, which was the integration on the last day. We chose a different approach for the second sprint because of our final. We finished a majority of our tasks early, and then we completed the last few after our final.
And as you can see, our stories focus on the work area and the world for the second sprint. And for the work area, we added like loop blocks, and we also added the functionalities that such like a loop blocks could include other blocks, and it also be able to detach. The other blocks could be able to detach from the loop blocks as well. And we have a reset button to reset the screen, clean out the workspace. And we have we also be able to remove blocks from the loop block. And for the world, we add more levels to the game comparing to the spring one. And we also update the world to the next level when a correct solution is detected. Also, we have run loop blocks and added a direction button to display the directions. And here we have a simplified version of UML diagram. Here, as you can see, there's a game class associated with two main panels, work area panel and the world panel, and the subclasses of the two panels expanded to the top. And if you want to see more details into the diagram, we can look at the next slide. As you can see, there are a lot of arrows like there. They represent the relationship between each class. Also, there are a lot of aggregation going on, which kind of indicates that the diagram suggests that we are likely to stay away from the pain zone a lot. And also we use GitHub for our version control, which enable us to collaborate effectively, and such as we developed our own branches, and when we were done, we created our own PRs. Then we had our teammates reviewed for approval.
For code, okay. So we mainly worked in world and the work area class. There we go. So for world, what we mainly implemented was the run function for loops. And that was similar to what we've done already, except we would pretty much iterate through the entire linked list until we hit a wall. And that was a function we already had. So we just created a flag which told us if there was a wall. And if there was, we would stop iterating through that loop.
So for the work area panel, to implement the loops, I created a loop block class, which extends the parent block superclass, which essentially holds another linked list of blocks to loop through. And then in work area panel, in order to spawn that loop block, I created another function which will take the location of the outer loop block, which holds all of them, and it will make that outline based on how many blocks are in the loop, and then it will go through the entire list and create those blocks that are inside the loop for visual representation.
All right, so for the trash can, it has a functionality to draw the trash can and show on the screen, and also it has a functionality to check if a given block or like connected blocks they're on the trash can or in the trash can. So as you can see here, we have a if conditional inside the mouth released function, and this conditional is mainly to check if a block or connected blocks were released within the trash can area. If it does, and then they're gonna be deleted. Yeah, that's it.
So for our pain zone graph, we only had two classes that were close to the pain zone, which was the singleton data source.
You can't see the slides.
Oh. Sorry. Yeah, as you can see, you only had two kind of close, which was the data source and the parent block. The rest were above at least 0.5.
For our code metrics, we had a total of 849 lines of code over 13 files with a total of 106 functions. Our effective lines of code was 672, and our logic lines of code were 468. This is only a slight increase from our last sprint because, as shown in our burn down chart, we completed a lot of tasks early and implemented a lot more functionality in the first sprint. So our lines of code only increased by a little bit. Our maximum cyclomatic complexity was in our run function in the world, just because it had to check so many conditions to see what needed to be run. And for our work area, our mouse press function also had a high cyclomatic complexity due to how many conditions it had to check for which block was being pressed. Our cost estimation chart can be seen here. Because our project was so small, we didn't have a great read on our cost estimation. However, we still got a lot of interesting insights from this chart. In the future, we had some ideas on what to implement. We wanted to implement sequence blocks, which will allow the user to name a sequence of blocks and have that run as one chunk, basically to emulate what a function does in code by combining a sequence of steps into one function under one name. In addition, we wanted to implement a slide bar so that the user can control what speed the spider moves at, so they can see how their code works at whatever speed feels best for them, just to further their understanding. We also wanted to implement a visual update just to make our user interface cleaner and more cohesive. And finally, because we had so many if conditions and like repeated steps, we wanted to optimize our code to have more functions and combine repetitive code. All in all, we made a really cool application that can be used for a lot of different people. So it could be younger, like middle school kids who have no experience with code, anywhere to older adults who wanted to learn how to code. We created a really intuitive user interface, and we also created a really rich user understanding through the visualization of the code through the spider. In terms of what went well, using an object-oriented programming language allowed us to work simultaneously and really minimize the amount of merge conflicts we had. Our taiga and the agile development process in general made it really easy to track each other's progress and check in a lot. Our GitHub allowed us to have version control, and our team communicated really effectively and were easy to reach. What did not go well is that we ran into a lot of bugs, and because of how little time we had, it made them pretty stressful, but we were able to achieve a really great application nonetheless. Yeah, thank you.
Thank you. Bye-bye.